Hi, my name is Abby Clark, and I'm going to be talking about paleoclimate shifts of Wisconsin, starting at the last glacial maximum and then moving into today. So, some of the things I'm going to talk about today is one, I'm going to go over the different study sites that I mentioned in this talk, the different proxy data that was collected at each site, what happened in the Pleistocene, the Holocene in the driftless area, Hell's Kitchen Lake, which is in north central Wisconsin, that's Holocene paleoclimate data. And I'm also going to get into some of the human implications because I ran into an issue where some of this paleoclimate data had been impacted by people. So the goal of my project was to understand how climate in Wisconsin has changed as glaciers retreated and land in central and north central Wisconsin was exposed. So where is the driftless area? The driftless area is a location in southwestern Wisconsin that has never been covered by ice throughout all the Pleistocene glaciation. Here you can see it's this little area right here that is characterized by a few outwash deposits from glaciers that are in some of the major rivers and streams, but otherwise there's no glacial deposits in these areas. So, north central Wisconsin site and the Cave of the Mounds site in the driftless area. Cave of the Mounds is a large cave located right here in southwestern Wisconsin. It was located about 18 kilometers from terminus of the Laurentide ice sheet during the Wisconsin glaciation. So it's a very good indicator of what climates were like right up against that moraine. And the north central site is up here in Hell's Kitchen Lake, pretty much right on the border between Wisconsin and the Upper Peninsula. I don't have it marked, but some of the other driftless area sites is the Brush Creek River Valley along the Kickapoo River. But because it's such a small valley, it doesn't actually have a location on Google Earth, but it's right over here. Kind of hard to see, but here's the Kickapoo River. And so what paleoclimate proxies were used at each site? So for Cave of the Mounds, we have uranium-thorium dating of speleothems from the cave. As we move into the Holocene, the driftless area, they use soil and pollen data collected from Brush Creek Valley and the soil deposits there. And then north central Wisconsin at Hell's Kitchen Lake, they use pollen and charcoal samples from varved lake sediments. So if you don't know what a varved lake sediment is, it's sediment layers in the lake that have been deposited every single year. So it gives a very accurate scale of what happened on a short time period. So the Pleistocene. Many of us know most of the Midwest, and especially most of Wisconsin, was covered by the Laurentide ice sheet during the last glacial maximum. And surrounding the terminus of these glaciers, you have vast areas of permafrost. So permafrost is permanently frozen soil, and these frozen soils, they store a lot of carbon and then obviously water. So what this meant for the driftless area is that they were looking to see when did this permafrost melt, and when would we have speleothem growth in the region. So here's a map of all the Pleistocene ice sheets that have been currently mapped. The one we're focusing on is this orange unit, which is the Wisconsin glaciation, and this little red circle here is an approximate location of where Cave of the Mounds is. As you can see, it's located right up against the end of the ice sheet from the green bingo. And so speleothem data. I'm sorry that this picture is a little blurry, but it's from one of the papers that I used. And you can kind of see it, that you can see each of these little bands correlates to a growth ring in these glaciers. And so what the paper by Batchelor et al. Did was went into Cave of the Mounds, cut a speleothem, and dated every single one of these rings, trying to see how did the permafrost act during the Wisconsin glaciation. If the permafrost had melted, there'd be an adequate amount of water and carbon in that water to bind with calcium. From calcium carbonate, it would drip into the Cave of the Mounds caves, and it would cause these speleothems to grow. If the permafrost never melted, there would not be enough water or carbon in any water, to form any speleothems. And so this was their data. And so what we're looking at is MIS2, which is the Wisconsin glaciation. Here's the delta 18 values. I don't know what B is. This is the 21st of June. carbon in the atmosphere, methane, and then the Cave of the Mountains uranium, thorium dating. So as you can see, there's no dates. If you come down here for all of the Midwest, Cave of the for speleothem growth, Wisconsin doesn't have any speleothem growth occurring during Wisconsin glaciation. So what does that mean for the driftless area in the Pleistocene? There was no speleothem growth, meaning that the environment was much colder than was originally thought. And this study, at least for the Cave of the Mountains and the driftless area, is hypothesizing that the Wisconsin glaciation was about 1 degree Celsius colder than the Illinois glaciation, which is the one previous. And so the vegetation area is not much of it. You're gonna have a lot of scrub grasses and shrubs. You're not gonna see any big trees or like flowering plants because the environment was just too cold. There wasn't enough water, and these are growing in frozen soil. This is typical of what you would see in the Canadian tundra today. So after that happened, glaciers started to retreat as the region warmed, and so glaciation, they say, officially ended in Wisconsin around 11,300 years before present. So as glaciers retreated, the driftless area began warming up, and that methane and carbon dioxide that was trapped in the permafrost was released, causing warming in the region, and it caused the migration of these tundra grasses to move north up into Minnesota, upper Wisconsin, and Canada. And so in driftless area, pollen and soil data were collected from the soil. And so this is a site along the Kickapoo River in Ontario, Wisconsin. It's characterized by these large bluffs of sandstone, mostly sandstone, interbedded limestone bedrock, a copy of the dolomite. And they took samples along these riverbeds here, where you're going to get the most soil deposition from the river and from any rust that's traveling from the northern parts of Wisconsin. So from this, combining soil and pollen data from two different studies by McDowell and Bartline and Webb, which are both published in the same large PDF of data collected in the driftless area for the Holocene, was able to come up with 3 different climate shifts between 9,000 years ago and today. So between 9,000 and 6,000 years, you see drying. You see less precipitation from what you saw from right when the glaciers began to melt. This is also caused to the warming in climate, but there's obviously no water because the glaciers have gone back up into northern Canada. And so then from the study from Bartline and Webb, which is one of the precipitation and temperature data, they actually classified the second zone as 6,000 to 3,000 years. But when you add in the soil data taken from the same sites, it restricts that age a little bit more, and you get the age range of 6,000 to 4,500 years before present. And here you have precipitation increasing, but you have temperature decreasing a lot. So instead of you seeing rain, you're seeing a lot more snow and ice as precipitation. And so instead of seeing more oak and trees, pines, as you would see in pictures like this, you're actually seeing the scrub grasses and the shrubs coming back down from Canada during this time period. They aren't sure when it happened or why it happened, but they're going off the pollen that they found in the soil. And then from 4,500 years ago to today, you see an increase in precipitation and a warming in temperature. So you see more oaks, pines, these hardwood trees from a forest in the driftless area. The soil data was actually constrained these ages because of when the dramatic shifts in soil layers happened. So the older soil, so any soil older than 4,500 years in this region, has a really distinct clay layer, where they had these wet hardwood forests that were trapping clay in the roots and forming these clay layers. From the modern soils, you see a lot more alluvium. So you see more gravels, more sands coming from outwash streams, and increased precipitation leading to more river floods. This graph is slightly blurry. I'm sorry, it was an old PDF, but this is an example of what the precipitation data looks like. So from 6,000 years ago, looking up here in the driftless area, this area is receiving just over 60 centimeters of precipitation per year. It's what their pollen data showed them. And today, it's receiving closer to 80 centimeters per year. So you can see there's about 20 centimeters difference in precipitation from 6,000 years ago to today. So moving up north into north central Wisconsin at Hell's Kitchen Lake. It's located right there. There's no good pictures of it, apparently, on the internet. So this is where Swain decided, he went up there and took a sediment core in the middle of the lake. He took a core that went up to back 2,000 years. And so for each one of those years, he went through and looked at pollen and charcoal that he found in each layer and analyzed them at the age. And then he used those pollen and charcoal data to come up with 6 different zones of climate shifts for north central Wisconsin in that 2,000-year period. And so the charcoal, that's important because it tells us, or tells like when fires happen. So that's a characteristic. If the dry season, you're going to have more fires occur, which is why it's important. So here are the 6 zones of climate shift. Zone 1, from 2,040 years ago to 1770 years before present, you have pine forests and low fires. This was considered a very wet environment. Zone 2, 1770 to 1150, you have more oak and birch, which is consistent with drying climates, and there's a lot more charcoal found in these sediments, so there's a lot more increased natural wildfires occurring. Zone 3, we have oak and birch from 1150 to 850. This one was an outlier because they expected there to be high fires again, but it appears that while precipitation might have increased or might have stayed the same, it's hard to tell because the pollen data shows that the same plants were present, but there's not as many fires happening in Zone 3. In Zone 4, 850 to 600, we start seeing human impact showing up with the abundance of paper, birch trees, and low fire. So I'll get into this a bit more later, but it's the introduction of the logging industry to north central Wisconsin. Zone 5, 600 to 150, we see an increase of pine trees with low fires. And what they actually found is that this Zone 5 is a zone of obviously increased moisture, but also a zone of cooling. So it actually correlates to the little ice age that occurred. And so they think that in north central Wisconsin, it brought more moisture and colder temperatures, making it harder for oak and birch trees to thrive during this time period. And then Zone 6, again, increased paper birch and charcoal found. And Zone 6 is actually today. So we have a moist climate in north central Wisconsin today. With the amount of charcoal found, it shows that there's a lot of fires, which doesn't make sense. And so they attributed Zone 6 to be entirely caused by the logging industry, and it actually isn't an indication of natural climate change. So implications of happening, there are multiple shifts going on in 2,000 years, which, looking at the driftless area, it was very long time shifts. We had from 20,000 years ago until present. And we're seeing a couple climate shifts. And north central Wisconsin, looking at pollen and charcoal, we see multiple shifts. The logging in the Schwalmgen-Nicolay forest is what caused a lot of those climate shifts, with paper birch showing up and the increased fires during a wet environment. And that contributes to natural fires that, of course, we're seeing in older, or closer to 2,000 years ago in north central Wisconsin, and the fires used for clear cutting forests today and burning. And so here's some pictures of it. The driftless area also had signs of human effects in it, where they found soil movement from agriculture. So some of that soil data did have to be thrown away because it just got mixed up. You couldn't tell the distinct layers, you couldn't tell the processes that soil formed in. And so a lot of this is happening because we're moving towards aesthetically pleasing vegetation. This stuff, like these trees, aren't natural in the region, and so the pollen that we could be seeing today doesn't necessarily correlate to the temperatures that we are seeing today. And then logging and burning. So this is an image from the Schwalmgen National Forest, or Schwalmgen State Forest, and that's all paper birch trees that they plant and cut down on a rotational schedule approximately every 10 years. So here are my references. Any questions?
So for the driftless area, I was just wondering if there's any geographical components as to why that area was unglaciated, because everything around it is glaciated. So I just thought it was kind of odd that little area was untouched.
I didn't find anything that said why, but I would guess it might have to do with the bedrock of the region. I know a lot of people went up to Baraboo, and that's quartzite there, so it's much harder to erode. And so it might have just been easier for the lobes of the glacier to go around that big area of hard quartzite instead of trying to cut right through it. Bryson.
You right at the end you mentioned about like the human interference with like pollen being introduced that's like not necessarily from that like environment or temperature. Do you think that's gonna like hinder further like research in the future because there's can be like these like erratics of like pollen from where they don't belong, or like what do you think about that?
I think it might, especially because I mean paper birch isn't natural in north central Wisconsin yet we find it. So I think knowing the history is also important with it. If you know that like this type of plant was planted here because people wanted it there and it's not natural in that area, it might like would answer that question, resolve it. But yeah, it definitely could, especially if pollen is like that's trapped in soil is being moved around, especially with agriculture. And that's what happened with a lot of these like last couple, which is why I thought it was important to include because like, the data that's more recent is being skewed by human impact and it's less telling of what the environments were actually like.
Great. We should move along though. Keep on schedule. So Hannah, you're up.